So let's speak a little bit about how hard is it to compute a Nash equilibrium in a normal form game. So let's start with a little history. John von Neumann, one of the founders of modern game theory, when he investigated zero-sum game, he proved the existence of equilibrium there, and he used what's known as the Brouwer fixed point theorem for that. And that led directly to algorithms for computing fixed points in such linear programs. First, there was Dantig's algorithm that really equivalent to what in modern days is called LP duality, and it's an exponential procedure, although in practice used widely. Of note is the Hachian polynomial time approach to solving linear programs, although in truth, in practice, it's not used as widely. It's not as practical a procedure. And when you go beyond zero-sum games, so when John Nash proved the existence of equilibrium for general sum games, he used the same fixed point theorem of Brouwer, and that also informed a series of algorithms, and they're noted there on the slide. And we will be looking at two of them, the Lemke-Hausen algorithm and a much more recent algorithm due to Ryan Porter and others. I will note that all of these are exponential in the worst case, and I will get back to that later. So let's start with the Lemke-Hausen algorithm, and let's start with a formulation of the Nash equilibrium for two-player games. It looks as follows. And this is a busy slide, but I'll walk you through it, and all will become clear. At heart are two sets of variables, the S's and the R's. The S's will denote will capture the mixed strategy used by the two players, player 1 and player 2. S1, for example, of S2K, for example, would be the weight or the probability with which player 2 plays action K in his mixed strategy. So the S1s and the S2s are the capture the mixed strategy of the two players, player 1 and player 2. R's are what are called the slack variables. And to understand their roles, let's look at, for example, this equation right there. So this applies to any action of player 1. For any action of player 1, we look at the value that the value that it gives with respect to the strategy of the other player. And so we look at all the actions available to player 2. We look at the payoff to player 1 given that he is playing a particular action J, and looking at that action of player of the other two, and normalizing it by the probability that the player 2 attaches to that strategy A2. And so if we look at this sum as a whole, this is the expected payoff for player 1 when playing strategy J, given that the player 2 is playing a certain mixed strategy S2. And it is what it is. And in general, if you look at all the actions that the player 1 plays, they will give different payoffs. What we want is for player 1 to best respond to that strategy of player 2. because in equilibrium, every player is best responding to the other. And so let's call U star 1 to be the payoff to player 1 in the Nash equilibrium. So in general, the payoff for player 1 when they play AJ will be no greater than the best response, but in general be less. So we're going to add this slack variable, as it's called, that will say this is how much player 1 is missing relative to their best response when they're playing strategy J. Those are the slack variables. And so now that will also give us a sense for this condition here. So the slack variables are always non-negative. And in a Nash equilibrium, they will be exactly 0, except when you speak about strategies that are actually played with 0 probability by the player. So now we talk about the S's. S's, as we said, speak about the weight in the mix that each player gives to their each of their actions in the mixed strategy they play. And so when player 1 plays strategy J with non-zero probability, it better be the case that he's best responding, namely that the slack variable is 0. And when they're playing with 0 probability, you don't care what the slack variable is because they're not playing that strategy at all. And you capture that by requiring that the product be 0. This is exactly the condition, and this is what makes it a linear complementarity problem. So I hope that's clear, and you can see now similarly for player 2. For player 2, we take each of their actions and we say if they're going to play it with some probability, then and we look at their best response here, given whatever player 1 is going to play their mixed strategy, and we're going to look at the slack variable here, and again we're going to require that their product be 0. In other words, the probability that they play J is non-zero just in case the slack variable is 0. Okay, so this is the nature of this mathematical optimization program, and of course I forgot to mention, but of course we want the S's to be a probability distribution. So they sum to 1 and they're all non-zero. All right, so this is our linear complementarity program. And now come Lemke-Hausen, who suggests to find a solution in a particular way. And we won't go over it, but the flavor of it is to initialize the S's and the R's a particular way. In fact, to artificially initialize them all to 0, and then one by one take them, it's called a pivoting procedure, take an S and an R in turn, alternating between the two, taking them out of the set that has the current value, and replacing it with a complementary variable. If it's an R, replacing with an S, and with an S, replacing an R, until you get an equilibrium. That's the general flavor of it, and in this lecture we won't go in more detail into the Lemke-Hausen procedure. But it is a procedure that looks very deeply at what a Nash equilibrium is, sets it up as a mathematical program, and then searches the space of variables in an informed way. Let's now look at a very different procedure, one that doesn't look in as much detail at the structure of equilibria, but compensates by performing heuristic search in a certain way. So let's look at it, and we'll look at it at 2 stages. The first step is to note that when you fix the support of a strategy profile, finding out whether there is a Nash equilibrium with that support is an easy problem. Remember that the support of a strategy consists of all the actions to which the player is giving non-zero probability in that mixed strategy. So let's look at this formulation. Let's look, and this will be limited to 2 players. And so let's look at all players in turn, for example, player 1, and let's look at every action of that player, for example, a sub I. We'll be looking for some mixed strategy P, mixed strategy profile for each of the players that will give us a Nash equilibrium, namely each agent will be best responding. And so for all actions in the support that we're considering, we'd want the agent to be best responding. So let's assume that the best response value is V sub I, just call it that number. Then we want AI to, in fact, to be a best response to the rest. And what we want is all other actions, any other actions not in support, to give us a value that's no greater than the best response. And we want it for each of the 2 players and each of their actions in the support. So that makes sense. And we want these to be a probability, so we want the probabilities in the support to be non-zero, we want the probabilities outside the support to be 0, and we want it indeed to be a probability distribution. This all makes sense. So this is a linear program. It's solvable in polynomial time. That is, theoretically, there's a polynomial time procedure. In practice, the procedures used are not polynomial in the worst case, but nonetheless effective. By the way, notice that we actually use the assumption that we're fixing the support here. Superficially, you might look at it and say, oh, I could do the same thing, but simply ignore the support part. Where are we using that really? Well, we're using it in the assumption that when we're best responding inside and don't have a profitable deviation, we're actually playing these PIs with probability, with a positive probability. Because if we playing the remaining strategy with 0 probability, in fact, it doesn't matter if we're best responding to it or not. And so this is where this assumption is hidden. So now we know that when we fix the support, we can solve the question efficiently. The fly in the ointment is the fact that there's an exponential number of supports to explore. And this is the second part. We need to simply now start exploring the set of support. And I won't go into details about how we do it, but the basic idea is the following. We will bias the support to supports that are close in size to one another. That is, we will not start by considering one agent looking at only 2 strategies among which he's randomizing, and the other agent looking at 17 strategies. We'll look at strategy profiles that are similar, whose support is similar in size. We'll also start with small supports and gradually move to larger supports. If we do that, and we involve and we use another trick called conditional domination, that is, we look at certain things we can ignore along the way, then what turns out that although the procedure is in the worst case exponential, as is the Lemke-Howson, in fact it performs in practice quite well, and in fact better than essentially all other procedures tried, including the Lemke-Howson. These procedures do have exponential worst case, and so the question is, can we do better? Are there procedures that are less than exponential in the worst case? And that takes us from the realm of complex algorithms to the realm of complexity analysis. So let's first remind ourselves a little bit about what complexity analysis looks like. We're looking at classes, whole classes of problems, such as the class of all games and the problem of determining a sample Nash equilibrium in those games. And we look at the how hard is that class as a whole. And so here is a small part of the complexity hierarchy. The class P, as it's known, is the class of problem for which a polynomial time solution is known. The class NP is the class of problems for which a solution can be verified in polynomial time, but not necessarily found in polynomial time. The class NP complete is the hardest among all the NP classes. That is the classes to which all NP problems can be reduced. And perhaps the biggest unsolved problem in theoretical computer science is the question of whether NP is different from P. It's widely believed to be, but has not been proved. So this is the general background we need to keep in mind, and now we can ask, well, where does the problem of finding a Nash equilibrium reside? In P? In NP? What can we say? Well, first of all, strictly speaking, we can't quite speak about it being in P or NP, because we know from Nash's theorem that a Nash equilibrium always exists. So the question, does it exist in Nash equilibrium, is trivial. The answer is yes. So we need to look at it a little differently. One way to look at it differently is to ask for Nash equilibrium with specific kind of properties. So for example, we can say, does it have unique Nash equilibrium? Or does exist a Nash equilibrium that's strictly Pareto efficient? Or is there a Nash equilibrium that guarantees a given player some minimum payoff? Or can we guarantee some minimum social welfare in a Nash equilibrium? Does there exist a Nash equilibrium that includes some pure strategy, some action of the player in it? Or conversely, that does exclude it? All of these and others are examples of questions that are provably NP hard. Okay, so that tells us something about the hardness, but still, we still ask about just finding a sample Nash equilibrium. How hard is that? So we've seen the algorithm. People have tried very hard to find algorithms computing a sample Nash equilibrium. And it does seem hard. The question is, can we somehow capture that formally within the complexity hierarchy? And for that, we need to introduce some new concepts. The essential concept is that of the new class of problems called PPAD, for polynomial parity arguments on directed graphs, introduced by Christos Papadimitriou in 1994. We won't go into detail, but just so you know the chronology, PPAD is a specialization of a class called TFNP, which is in turn was a specialization of a problem called FNP. Going in detail here is beyond the scope of what we want to speak about, but it does help us now position the complexity of finding a sample Nash equilibrium in the complexity hierarchy. And again, we have the class of polynomial time problems, of problems that can be verified in polynomial time, with these being the hardest among them. And given that, PPAD turns out to reside somewhere within this class. Now again, we don't know whether this entire class does not collapse and all become one and the same. It's widely believed that it does not, but proof doesn't exist. However, we do know that PPAD lies someplace in between P and NP. Now, what does that have to do with the problem of computing a Nash equilibrium? Well, that's where the following theorems come in. Originally, it was shown that the problem of computing a Nash equilibrium is complete for this class PPAD. That is, it's the hardest among all problems in that class. Initially proved for 4 players, then for all 4 games with 3 or more players, and then finally in 06 for all classes of games. And so we widely believe that the problem is not polynomial, cannot prove it, but we do know where it resides within the complexity hierarchy that we are familiar with.